Hello everyone, myself Dr. G. SIRISHA, Associate Professor, Department of PC. Today I am going to give a lecture on applications of the diode. Contents. Rectifiers. Rectifiers are of three types, that is half-wave rectifier, full-wave rectifier, bridge rectifier. Next, rectifier with the filters, clippers, clampers, and comparisons of clippers and clampers. First, we will see what is meant by rectifier. So rectifier is an electronic device which converts AC into a pulsating DC. This can also be called as a rectification. So to get the pure DC, the pulsating DC is passing through a filter. What is meant by pulsating DC? The pulsating DC is nothing but some unwanted AC components are going to be present in output of the rectifier. That AC components are called as pulsating DC. What is the need of rectification? Where we can use? For example, if we consider all the electronic items or the gadgets that works with DC power supply. To get this DC power supply, we are going to convert a AC voltage into a pulsating DC voltage with the help of using the rectifiers. Rectifiers are of three types, that is half-wave rectifier, full-wave rectifier, and bridge rectifier. First, we will see what is meant by half-wave rectifier. Here, the name itself indicates that half-wave rectifier. Means the rectification is going to be done only for the half-wave. For example, here you can see the circuit diagram. The circuit diagram consists of AC input which is applied to a transformer. The transformer, what we are taking here is a center tapped transformer. To this secondary winding of the center tapped transformer, a diode D is connected. To the cathode terminal of the diode, resistor R is connected, and across the resistor, we are taking as an output. So to the primary winding of the transformer, we are giving the AC input signal, that is 230 volts AC 50 Hz frequency. And towards the secondary transformer, we are connecting the diode. And next, continue with the load resistor, and across the load resistor, we are taking the output signal. For example, if we consider the input signal that is of having AC positive cycle and negative cycle. So we'll see the operation during the positive cycle. So during the positive cycle, the diode D having the anode and cathode terminal. So that anode terminal is supplied with a positive voltage and cathode terminal can be taken as a ground terminal. As we know that the principle of the diode operation, if the voltage across anode is greater than the voltage across cathode, then the diode will be acts as a forward bias. So here, diode anode terminal is supplied with the positive voltage and the cathode is supplied with the negative, that is 0 voltage. So we can say that the voltage across anode is greater than the voltage across cathode. So the diode will be acts as a forward bias. When the diode will be acts as a forward bias, so it can be considered as a short circuit. When the diode acts as a short circuit, then the input signal flows from the diode is going to be flown across the load resistor and taken as an output, that is a positive cycle. In the V0, you can see for the first half cycle, the output signal is same as input. Means you can say that V0 is equal to Vs, that is only the positive cycle. And next, it is continued with the second cycle, that is negative cycle. If we apply the negative cycle to the anode terminal of the diode, means we can say that the voltage across the anode is with the negative polarity, that is a negative voltage. Means we can apply all the instantaneous voltages to the instantaneous negative voltages to the anode terminal of the diode. So now the potential at anode is negative and the potential at the cathode is 0. So here it satisfies that voltage across anode is less than voltage across cathode. If this condition was going to be satisfied, then we can say that diode is going to be work under reverse bias. When the diode is under reversed bias, this will be acts as a open circuit. So as the input signal doesn't flow across the load resistor, then at this negative cycle, we can say that the output is 0. So here in the output waveform, you can say that for the input as a negative cycle with the Vs, then the output can be considered as a 0. So this can be seen in the waveform also. That is, we are going to take 0 volts as a reference voltage. Okay, and the positive signal is going to be taken as a plus Vmax, that is the maximum positive voltage, and the negative cycle is going to be taken as a minus Vmax, that is a maximum negative voltage. So for every instantaneous voltage of positive and for every instantaneous of negative voltage, the diode D is going to be responded. So for during positive cycle, for from 0 to Vmax and from Vmax to 0 voltage, the diode D is going to be acts as a forward bias and gives the output signal, that is as a positive cycle. And similarly, coming to the negative cycle, when the negative cycle is changing from 0 to minus Vmax and from minus Vmax to 0, that is, we can consider this is the negative cycle. If it is applied to a diode D, then diode will be acts as a reverse bias and it is a open circuit and the output is 0. So here, as you observe the output waveform, that is the resultant waveform, only the diode is going to be conduct for only one half cycle and the remaining other half cycle you can consider as a 0. So this is nothing but half wave rectifier. So here the half wave rectifier is nothing but it is a circuit passes just one half of each complete sine wave of the AC supply in order to convert into a DC supply. Next, half-wave rectifier using filter. When you observe the output of the half-wave rectifier, for only one half cycle, the diode is going to be conduct, and for other half cycle, the diode is not going to be conduct. So the output of the half-wave rectifier is not a desirable one. Why? Because the most of the cycle, half cycle is going to be completely wasted and it is going to be completed, taken as a 0. And we can say that the output of the rectifier is a pulsating DC. Means some unwanted components are going to be present in the output of the half-wave rectifier. To remove these unwanted AC components, the half-wave rectifier is going to be designed with filter. So here, using the filter, this filter will remove some unwanted components present in the half-wave rectifier and give the smoothing output. That is, you can say that charging, you can see the output, that is charging and discharging of the capacitor, which removes the unwanted ripples present in the output of the half-wave rectifier. So this can be possible with the help of using the capacitor called as a smoothing capacitor. So the filter is capacitor. Not only the capacitor we can use as a filter, we can use the inductor also. And we can use a combination of L and C, and also we can use the combinations of LCL or CLC filters. Those filters can also be called as a pipe filters. So here, during the positive cycle of the rectifier output, half-wave rectifier output, the capacitor is going to be under charging states. Okay, this can be seen in the waveform. So whenever it reaches to a maximum voltage, again the capacitor is going to be under discharging state. This discharging state can be continue until the waveform gets the maximum value. When the waveform is going to be reached to a maximum value, that is output of the rectifier, again the capacitor will be in completely full charge. Whenever it reaches to a maximum voltage, again the capacitor is going to be discharged. And this voltage we call it as a capacitor voltage. The next one, full wave rectifier. So coming to the full wave rectifier, so here name itself indicates that the rectification is going to be done for 2 complete cycles. So the drawback of the half-wave rectifier, what we can see is for only one half cycle, the rectifier is going to be conduct, and remaining other half cycle, it is not going to be conduct. It gives a 0 as an output. So here the transformer utilization is not effectively used in half-wave rectifier. To fulfill the complete transformer utilization and to get the complete waveform without any output signal as a 0, you are going for full wave rectifier. So here name itself indicates that the rectification is going to be done for complete cycles of the AC input signal. So here the full wave rectifier uses the 2 diodes. So among these 2 diodes, one diode is used for one half cycle and the other diode is going to be used for other half cycle. The circuit diagram is going to be seen here. So here AC input signal is going to be given for the primary winding of the center tapered transformer, and toward the secondary secondary winding. The secondary winding is divided into three parts. The first A part is given to, that is a phase, and the B is going to be considered as a minus phase, and C is taken as a neutral. So as it is a center tapered transformer, A to C having the equal divisions and C to B is also having the equal divisions. A to C can be considered as a positive and C to B can be considered as a negative. So that's, we can say that even half cycles, and next one is the odd half cycles. And here a positive signal is applied to the diode D1, and similarly the same positive cycle is applied to the diode D2 also. Now the point A is supplied with the positive polarity and B is supplied with the negative polarity. If for the first half cycle, that is during the positive cycle, diode D1 anode terminal is supplied with the positive terminal and cathode is supplied with the resistor that is connected to the ground. And next, diode D2 anode terminal is connected with the negative polarity and the cathode terminal is connected with the ground. So you can say that the potential at anode terminal of the D1 is greater than cathode terminal, and the potential at anode terminal of D2 is less than cathode terminal. So using these conditions, we can say that diode D1 will be under forward bias and diode D2 will be under reversed bias. This can be taken for the positive input cycle. So whenever diode D1 is going to be acts as a forward bias, you can say that diode D1 is in short circuit. And similarly, diode D2 can be replaced as an open circuit. So whenever D1 is acts as a short circuit, the applied input signal is flowing towards the RL through the polarities plus to minus, and it is going to be taken as output signal. So means the output is going to be taken across the RL. So the direction of the output is taken from plus to minus polarity. So here you can say that during positive half cycle, diode D1 is going to be conduct and diode D2 is going to be in non-conduction state. So the current is flowing only through the diode D1 and the output voltage can be taken across RL, that is equal to the input, that is V0 is equal to Vs. And similarly, coming to the negative cycle. So if the polarities are supplied with the negative cycle, means you can say that the potential A is with the negative cycle and the potential B is with also negative cycle, but already the polarity of the B is that is minus phase. So minus into minus will become the plus, so that the anode terminal of the diode D2 is supplied with the plus and anode terminal of the D1 is supplied with the minus. So here you can say that the potential across the anode terminal of D1 is less than cathode terminal and the potential at anode terminal of D2 is greater than the potential of cathode terminal. So here you can say that diode D1 will be acts as a reversed bias and diode D2 will be acts as a forward biased. When diode D1 is in reversed bias, it can be replaced as an off circuit, and whenever D2 is as an forward bias, it can be replaced as a short circuit. Whenever it acts as a short circuit, the output signal is going to be flown through the RL using the same direction, that is from plus to minus only. So here during negative cycle, diode D1 is in non-conducting state and diode D2 is in conducting state. So here whenever D2 is in conducting state, the negative half cycle is going to be converted into a positive cycle with the polarities that is plus to minus. By following the direction plus to minus. This can be possible that here by using the principle of the diode operation. Diode is the electronic device which allows a flow of current only in one direction. Means the output has to be taken only from plus to minus polarities of the RL only. So that it uses only the one direction. So that during positive cycle also D1 conducts, D2 not conducting. So the output is flowing from plus to minus the single direction only. And during negative cycle, D1 is in reversed bias and D2 is in forward bias, means the output is also going to be flowing from plus to minus only through the RL, means during positive cycle it is maintaining the same direction, and during negative cycle also it is going to maintain the same direction, so that you can say that full wave rectifier is going to be converted for complete cycles of input signal, that is for the half wave rectifier is going to conduct for positive cycle as well negative cycle also. So this is the resultant waveform you can see here. So 0 volts is the reference voltage and plus Vmax is the maximum voltage. So what are the drawbacks in the half wave rectifier can be overcome with the help of using the full wave rectifier. So here coming to the drawback of the half wave rectifier, it is going to be conduct only for the 1/2 cycle. But here you can see that all the complete full cycles are going to be conduct. Coming to the efficiency of the half wave rectifier is going to be taken as only the 40%. Why? Because only it is going to conduct for 1/2 cycle. But whereas coming to the full wave rectifier, it is going to be conduct for complete full cycles of the input waveform. So that the efficiency is going to be double. That is, efficiency is given as 80% for the full wave rectifier. That is 81.2%. Next, a ripple factor. So coming to the ripple factor, the unwanted components are going to be taken as a very large amount of the half wave rectifier. But whereas coming to the full wave rectifier, those ripples are going to be reduced as it is going to be conducting full cycles. So the ripple factor is reduced from 1.21 to 0.48 as a ripple factor. Next, we will see the full wave rectifier with filter. As we can say that the DC output is to be a straight line. So, but as we see the output of the full wave rectifier, it is having some pulsating DC. So, those unwanted components present in the full wave rectifier output is going to be filtered by using a capacitor filter. The example of the filter, we are taking it as a capacitor. Not only with the help of the capacitor, we can also remove the unwanted AC components with the help of inductors also, or LC filters, capacitors, pi filters also. So the example of the filter we are taking here is a capacitor filter. So now the output of the rectifier is going to be connected with the capacitor, and next capacitor is to be connected with the RL, and here the output is taken across the RL resistor. So the same AC input signal is applied to primary winding, and through the secondary winding, the diode D1 and D2 is going to be connected, and the output of the D1 and D2 is a complete full cycle. That full cycle is going to be given as an input to the capacitor. As we have already seen in half wave rectifier operation with the filter, the same operation is going to be taken here also. So here, whenever the capacitor is going to be considered as a charging, that starts from 0 to maximum value. Whenever it reaches to a maximum voltage, again it is going to be discharges. Again, if it reaches to a maximum voltage, that is to a charging. And again, it reaches, whenever it reaches the maximum, again it discharging. So here, so as compared to the half wave rectifier, some unwanted ripples are going to be removed with the help of using the capacitor filter. Next type of the rectifier we are discussing here is bridge rectifier. So here some disadvantage we can see for the half wave rectifier, full wave rectifier, that is using of center taper transformer. So in order to use the center taper transformer, there will be some complexity in the circuit. So to avoid that problem, and the usage of the transformer is also bulky and it is also costly. To overcome all these problems, we are going to use the bridge rectifier. So bridge rectifier is going to be used with the normal transformer. But here the usage of the diodes are going to be increased. In a full wave rectifier using center tapered, there itself we are using only the 2 diodes. But now here we are going to use a 4 number of diodes. So here you can see that advantage of this bridge circuit is that it does not require a special center tapered transformer, thereby reducing its size, complexity, and the cost also. So this is the circuit diagram for the bridge rectifier where we are using diode D1, D2, D3, D4. Here name itself indicates that bridge. So diode D1, D2, D3, D4 are going to be connected in a bridge type of connection. So that's why this rectifier is going to be called as a bridge rectifier. To this bridge rectifier, we are giving the input signal as a AC input signal, and the output of these diodes are going to be taken across the load resistor RL. Next, we'll see the operation of the bridge rectifier. So here you can see the operation of the bridge rectifier. So with the filter also. So first we'll see the operation with the rectifier without the filter, and then we continue with the filter. So here, whenever input signal is applied to a bridge rectifier, the positions of the diode D1 and D2 are in same positions, and the positions of the diode D3 and D4 are in same positions. When an AC input signal, that is a positive half cycle, is applied towards the pointer, upper point of the diode D1 and D2, that is anode terminal of the D1 and cathode terminal of the D4. The positive cycle is applied to anode terminal of the D1 and cathode terminal of the D4. The same positive cycle is applied for anode terminal of the diode D2 and anode terminal of the diode D3. So here, whenever the positive cycle is applied, the polarities of the D1, D2, D3, D4 can be considered as D1 is with the potentials of plus and minus, and D4 is with the plus and minus, and D2 is with the minus and plus, and D3 is with the minus and plus. So here you can see the polarity, that is the plus and minus, has been taken with the bridge rectifier. So whenever a positive cycle is applied to all the diodes D1, D2, D3, D4, now the D1 and D2 is supplied with the positive cycle, and D4 D3 and D4 is supplied with negative cycle. So whenever a positive cycle is applied to a bridge rectifier, D1 and D2 will be acts as a forward bias, and D3 and D4 is going to be acts as a reversed bias. When D1, D2 acts as a forward bias, it acts as a short circuit. Then the applied positive pulse is going to be flow towards D1 and D2 and towards the resistor RL. And next, whenever a negative cycle is applied, so diode D3 and D4 will be acts as a reversed bias, acts as a D3 and D4 will be acts as a forward biased, and D1 and D2 will be acts as a reversed bias. When D3 and D4 acts as a forward bias, the negative cycle is flowing from diode D3 and D4 through the load resistor using the same direction of the previous current. Okay, so here during the positive cycle, diode D1 and D2 will be acts as a forward bias, and during negative cycle, diode D3 and D4 will be acts as a forward bias. Means here only the two diodes are going to be conduct for a positive cycle, that is D1 and D2, and remaining the D3 and D4 is in non-conducting state, and gives the output signal, that is V0 is equal to Vi. And during negative cycle, D1 and D2 will be acts as a reversed bias, and it acts as an open circuit, and it is in non-conducting state. And similarly, D3 and D4 will be under forward biased, it will be under conducting state, and it will be acts as a short circuit, and output is going to be flow from load resistor, that is with respect to positive and negative potential. So here the output of the bridge rectifier is same as full wave rectifier only. So here, in order to remove the unwanted AC components present in the full wave rectifier, this bridge rectifier is again connected with capacitor. This capacitor can be called as a smoothing capacitor to make the output as much as possible as a smooth without any unwanted components present in the output of this rectifier. So here the same concept we can use here also, that is the capacitor will be under charging and discharging. Whenever the output voltage of the full wave rectifier is in maximum state, it is going to be charging. Whenever the voltage is decreasing, the capacitor is also going to be discharged. Whenever the voltage is increasing, output voltage is increasing, the capacitor is also going to be increases. And whenever it discharges, the capacitor is also going to be discharges. So this is the resultant output waveform, and you can see clearly about the charging and discharging waveforms of the capacitor. So here the main advantage of the bridge rectifier is usage of 4 diodes, and we are using the normal transformer to get the operation. So instead of using the center tap transformer, the bridge rectifier is going to be used with the normal transformer. And the efficiency is also same as full wave rectifier only. That is a 81.2%. And the ripple factor of the bridge wave rectifier is going to be taken as a full 0.48. So here, whatever the drawbacks seen in the half wave rectifier can be overcome with the help of using full wave rectifier as well bridge rectifier. Next one, comparisons of the rectifiers. There are many parameters to compare the rectifiers. As we know that rectifiers are half wave rectifier, center tapped rectifier, that is full wave rectifier, and bridge rectifier. These 3 rectifiers are going to be compared with the number of parameters. The parameters can be seen here as the number of diodes, transformer tapping, peak inverse voltage, maximum efficiency, average or DC current, DC voltage, RMS current. During the operation of these rectifiers, all these parameters are going to be considered. For example, if we consider the first parameter, the number of diodes. Number of diodes are to be used for the half wave rectifier is only 1. Why? Because the name itself indicates that half wave means it is going to conduct only for 1/2 cycle. That's why it uses the 1/2, 1 diode. Next, coming to the center tapped full wave rectifier, the number of diodes are 2 and the bridge rectifier is with 4. So coming to the next parameter, transformer tapping. So that is center tapped transformer. So half wave rectifier doesn't require the center tapped transformer, but full wave rectifier center tapped, it requires the transformer tapping. Here name itself indicates that center tapped full wave rectifier means it compulsory is going to use the center tapped. And next, bridge wave rectifier is not using the center tapped. The next one is peak inverse voltage. The peak inverse voltage of the half wave rectifier is taken as a VM. And next, for the full center tapped full wave rectifier, it is 2 VM. And the bridge rectifier is with VM. Next, coming to the efficiency. The efficiency of the half wave rectifier is given as only 40.6%, which is not a desirable one, so that it cannot be used for any practical applications. Coming to the center tapped transformer, center tapped full wave rectifier, the efficiency is going to be double as compared to the half wave, that is 81.2%. The same can be applicable for the bridge full wave rectifier also. Next, average of the DC current. So whenever the output is going to be taken across the half wave, full wave rectifiers, the average DC current we are going to take in as a Im by pi. And for the center tapped, 2 Im by pi. And for the bridge, 2 Im by pi. So Im by pi is going to be taken. Why? Because only it is going to conduct for 1/2 cycle. And whereas 2 Im by pi is going to be taken. Why? Because it is conducting for both the cycles. That's why Im is replaced with 2 Im for center tapped and bridge rectifier, full wave rectifier. Next, the DC voltage is given as Vm by pi. Vm is the maximum voltage and Im is the maximum current. So here for center tapped, as it is conducting for both the cycles, the DC voltage is taken as 2 Vm. And for the bridge also, it can be taken as 2 Vm by pi. Next, RMS current. The RMS current of the half wave rectifier is given as Im by 2. As we are seeing that the output of the half wave rectifier is having with some unwanted AC components. Those unwanted AC components are going to be calculated by using the RMS current. That current is given as Im by 2. And for the full wave center tapped rectifier, it is Im by root 2. And for the bridge is Im by root 2. The next one is clippers. So here, till now we discussed about the applications of the diode, that is as rectifiers. Now using the same diodes, the diode can also be accessed as clippers. The clippers is somewhat equal to the rectifiers only. It is similar to rectifier only. So rectifiers means converting an AC signal into a pulsating DC. But coming to the clippers, here the clipper circuits are also an electronic circuit which are used to remove the part of a signal that is above or below some defined reference level. For example, if you consider the output waveform of a rectifier, or if you consider the input signal, sinusoidal signal to a clippers, if some portion of the signal is going to be removed, that can be either above part or the below part, or any part of the signal is going to be removed in the sine wave signal. So those can be done with the help of using the clippers. Means we are removing the unwanted portion of the signal, and the remaining portion of the signal is going to be considered as a desired signal. So here the clippers can also be called as a limiters. It can also be called as a amplitude selectors or slicers. The best example of the clipper is going to be taken as a half-wave rectifier. For example, if you observe the output of the half-wave rectifier, for one cycle it is going to be conduct, and remaining other cycle it is not going to be conduct. Means for the positive half cycle we are going to consider as a desired signal, and the negative half cycle we are taking it as a 0. Means nothing but it is going to be, the negative cycle is going to be clipped off there. Means the desired portion of that waveform is only the positive cycle, and the undesired portion is going to be cut off with the help of using a clip. So that's why we can say that the best example for the clipper is a half-wave rectifier. Just can be considered as a simple example to understand the concept of the clipper. Now, the types of clippers. The clippers are going to be considered as two types, that is series clipper and parallel clipper. Series clipper means, here name itself indicates that diode is in series with the load. And coming to the parallel clipper, the name itself indicates that the diode in parallel with load. So now we will see the detailed classification of the clippers, that is types of the clippers. So clippers are going to be classified into a unbiased clippers and a biased clippers. So this can be applicable for the series clippers as well parallel clippers also. So under unbiased clippers, so it is again divided into two types, that is unbiased positive clippers and unbiased negative clippers. And similarly, biased clippers are also going to be divided into two, that is a biased positive clippers and a biased negative clippers. So first we'll see some unbiased positive clippers, circuit diagrams, its operation and waveforms also. So this is the unbiased positive clipper. Name itself indicates that unbiased. We are not giving any reference voltage, the DC reference voltage to the circuit diagram. And the name itself indicates that it is a positive clipper. Means the positive portion of the signal is going to be clipped off, and the remaining portion signal is going to be taken as an output waveform. This can be possible with the help of the circuit diagram. So we can design the positive clipper as a like this. This comes under series clipper. Why? Because the diode D is in series with the load R. So the input signal we are applying is a sinusoidal signal having the polarities, that is a plus V as a maximum voltage of a positive cycle, and minus V is the maximum voltage of the negative cycle. So if we apply this positive cycle to cathode terminal of the diode during positive cycle, so what happened? Here the diode D is cathode terminal of the diode D is applied with the positive polarity, and anode terminal of the diode D is with 0 voltage. So now the diode will be under reversed bias. The diode will be under reversed bias, and it will be acts as an open circuit So when the diode acts as an open circuit, there is no output, that is V0 can be considered as 0. So in the waveform, you can see that for the positive half cycle, the output is taken as a 0. And similarly, the next cycle is going to be applied to a diode cathode terminal, that is the negative cycle. So whenever the negative voltage is applied to cathode terminal of the diode, now the diode D will be under forward biased. So it can be acts as a short circuit, and the same negative voltage is flowing towards the load resistor R. And finally, you can say that V0 is supplied with the negative voltage. And this can be continued for the next positive cycle also. During the positive cycle, diode D is in reversed bias, in that acts as an open circuit. And whenever a negative cycle is applied to a diode, and the diode will be acts as a forward bias and gives the output signal as a negative cycle. So if you observe the input and output waveforms, the positive portion of the signal is going to be clipped off, and we are going to consider only the negative portion of the signal. So here the name justifies that positive clipper. Means the positive portion of the signal is going to be clipped and the remaining negative cycle is going to be considered. This can be possible when the diode is going to be connected with respect to cathode to anode. The next example we'll see unbiased negative clipper. So here you can see that unbiased negative clipper, that is unbiased means there is no reference voltage connected here and in the circuit diagram, and the name itself indicates that negative clipper means the positive portion of the signal is going to be taken as an output and the negative portion of the signal is going to be clipped off. So the input signal applied here is sinusoidal signal, which consists of positive and negative cycle with the maximum voltage as plus V and minus V. A positive signal is applied to a resistor, the diode, to the cathode terminal of the diode. So diode will be under off state, diode D will be under off state, that is it can access a reversed bias. So the output signal can be taken as V0 is equal to 0. So when it acts as a reversed bias, it will be acts as an open circuit. So you can say take that output V0 is equal to Vi. That is a positive cycle. So here whenever the input signal is supplied with the negative cycle, so the diode D will be acts as a short circuit. Now it will be under forward bias, it will be acts as a short circuit, and the output is going to be considered as a 0. So here, if you observe the output waveform and the input waveform, only the positive portion of the signal is going to be considered and the negative portion of the signal is going to be clipped off. So that's why we can say that it is a unbiased negative clipper. In the similar way, we can study an examples of different examples of a clippers. So here, coming to the practical circuits, if we consider this is as a positive series clipper. So when you give the input signal with plus Vm as a maximum voltage to the diode cathode terminal of the diode D, we are seeing that diode D will be acts as a reversed bias and it will be acts as an open circuit. Whenever it acts as an open circuit, the output voltage V0 is equal to 0. But coming to the practical applications, as there will be some leakage current is flowing towards the diode, that leakage current is going to be considered and this is going to be drawn, that is above the reference voltage, that is a 0 voltage. Means a small portion of the output positive voltage can be seen across the positive cycle. This can be seen in the practical applications. Whereas if a negative cycle is applied to the diode D, now the diode D will be acts as a forward bias and the output will be equal to the input. The same way we can see for the negative series clipper also. During the positive cycle, the output is equal to input, and during the negative cycle, the output must be a 0, but due to practical, that is the diode will be acts as a practical resistor. Diode will be acts as a practical diode. So there will be a voltage drop across this diode, and whenever it acts as a reversed bias, the leakage current is going to be flow towards this diode and the output will be with some negative polarity. So these are the examples of the few examples of the clippers. And the next class is going to be continue with clippers with biased voltages.